Section. Introduction. We're here to introduce a new concept within the realm of large language models, LLMs, like GPT-4 and PaLM-2. These models have been game changers in how we understand natural language processing, and their impact has been felt across several industries. Despite their many advantages, LLMs are not without limitations. One significant challenge is their inability to handle a large volume of tokens. For example, GPT-4 can manage only 32,000 tokens at a time. As the conversation progresses, the model has to keep track of all user inputs and prior responses and craft replies based on this information. Trying to feed all of this into the model can exceed its capacity, resulting in errors and a loss of conversational context. There have been efforts to address this using neural memory mechanisms. These mechanisms act like a storage and retrieval system for information from past interactions. However, they can pose difficulties in storing, retrieving, and manipulating historical information, especially in tasks requiring complex reasoning. This is primarily because they do not structure the information, and their manipulation of stored data is not symbolic, relying on vector similarity calculations that can lead to error accumulation. To overcome these challenges, we propose the use of databases as a new form of symbolic memory for LLMs, an approach we've called ChatDB. This framework comprises two parts: an LLM controller and its memory. The LLM controller, which could be any commonly used LLM, is tasked with overseeing read and write operations to the memory. The memory's role is to store historical data and provide information to aid the LLM in responding to user input. In ChatDB, we've chosen to use databases as symbolic memory, allowing for the structured storage of historical data using a symbolic language, such as SQL statements generated by an LLM. Using a database in this way can be particularly beneficial in situations where accurate recording, modification, querying, deletion, and analysis of past data are required. For example, a store manager maintaining daily sales records would find this approach more suitable than using plain text or matrices. A database enables accurate operations like data insertion, deletion, update, and selection using SQL statements. So, by employing databases as external symbolic memory, we can enhance the accuracy and efficiency of managing and manipulating historical data, greatly improving LLM performance. Additionally, in the ChatDB framework, we've introduced a method called the chain of memory approach. This method simplifies user input into a sequence of intermediate memory operation steps leading to the final results. Each step consists of one or more SQL statements. This process helps to break down complex problems into manageable memory operations, reducing problem-solving complexity. Our ChatDB system brings several new contributions to the field of LLMs. First, it introduces the use of databases as external symbolic memory for LLMs, offering a structured way to store historical data and perform symbolic and complex data operations with SQL statements. Secondly, the chain of memory approach allows for effective memory manipulation, which improves the overall performance of ChatDB, especially for handling complex database interactions. Finally, our experiments show that providing LLMs with symbolic memory enhances their multi-hop reasoning capabilities and reduces error accumulation. As a result, ChatDB significantly outperforms ChatGPT on a synthetic dataset. Section summary. Large language models, LLMs, have limitations in handling multi-turn interactions due to their input token limit. To overcome this, the authors propose using databases as external symbolic memory for LLMs, allowing for structured storage of historical data and enabling complex data operations using SQL statements. Their ChatDB framework also introduces the chain of memory approach, which converts user input into multi-step intermediate memory operations, enhancing the performance of ChatDB and improving its multi-hop reasoning capabilities. Section. Related work. In the realm of related research, there are several key areas we should examine. These include memory-augmented large language models, LLMs, reasoning capabilities of LLMs, the interplay between LLMs and databases, and tool using LLMs. Beginning with memory-augmented LLMs, models like GPT-4 and PaLM-2 have shown impressive abilities in reasoning and decision-making. Their limitation, however, lies in their restricted context window size. For instance, GPT-4 can only handle up to 32,000 tokens at a time. To overcome this hurdle, memory-augmented LLMs were developed. They introduce a memory component, which allows these models to retain essential data and manage more extended text inputs beyond their original context window size. Another enhancement came with the concept of retrieval augmented in context learning. It employs retrieval models to gather relevant information that is then incorporated into the LLM as a prompt. Models like AutoGPT and generative agents use this method, employing a memory module that directly stores the text prompt, allowing the agent to maintain a record of its interactions. The field has seen other advances, like the Neural Turing Machines, NTM, which combines recurrent neural networks with external trainable memory resources. There's also the Gated Graph Sequence Neural Network, GGS nitrogen mononitride, that uses graph structures for more meaningful outputs, and the Recurrent Memory Transformer, RMT, which includes additional memory tokens to handle and exchange information across long sequences. Next, let's talk about the reasoning abilities of LLMs. Traditionally, these models have struggled with intricate reasoning tasks. Previous techniques aim to improve reasoning through the inclusion of specially designed supervisory signals or through fine-tuning. Recent methods, however, focus on in-context learning. A notable example here is chain of thought, COT, which presents the reasoning process of solving sample problems to the language model, significantly boosting its reasoning capabilities. Moving on to the interaction between LLMs and databases, DBs, LLMs have proven excellent at generating code, including Python code, Excel execution commands, and SQL for databases. Projects like ChatExcel use LLMs to generate Excel commands, while Binder employs an LLM to carry out various functionalities using Python code bound with an API. Another impressive model is SQL PaLM, which significantly outperforms other text-to-SQL methods. Our proposed ChatDB system, however, presents a different approach. It views the database as an external memory module for the LLM, using it to read and write essential data, thereby enhancing the reasoning process. Lastly, from a tool-using perspective, ChatDB can be seen as an LLM utilizing databases as a tool. A relevant example here is Toolformer, which educates the language model to use external tools via APIs to solve problems. Another example is AutoGPT, which enables language models to perform impressive tasks using a search engine. The advantage of ChatDB, which uses a database as an external tool, is that it allows the language model to keep accurate records and utilize historical data, which is highly beneficial in solving complex problems, particularly those needing precise historical data for reasoning. Section summary. Memory-augmented large language models, LLMs, have powerful reasoning and decision-making abilities, but are limited by their context window sizes. Retrieval-augmented in-context learning and recurrent memory transformer, RMT, are some of the methods used to enhance the reasoning ability of LLMs. ChatDB is a proposed system that views databases as an external symbolic memory module for LLMs, allowing for more accurate reasoning results by leveraging the database for reading and writing essential data information via chain of memory. Section, ChatDB. We'll start off by briefly introducing the task and environment for our proposed system, ChatDB. We'll then provide a detailed overview of the ChatDB framework, with a special emphasis on its key component, the chain of memory. Approach. The task we've set for ourselves involves responding to user inputs given in natural language, using information from an external database, if such tables exist. Our goal is to manage the symbolic memory, or external database, to meet the user's needs. Imagine a store manager issuing commands like, record this data, change these details, look up this information, or remove this entry. In response, we want our system, ChatDB, to perform the relevant SQL operations such as insert, update, select, or delete on the right tables in the database. This often means working with multiple tables at once. Let's take a closer look at how ChatDB works. There are three main stages in our framework: input processing, the chain of memory, and a response summary. The process begins with interpreting the user's input. If the request requires us to interact with the memory database, ChatDB generates a series of steps using language learning models, LLMs, to do so. If not, the LLMs simply generate a direct response. Next, we have the chain of memory stage. This is where ChatDB interacts with the symbolic memory, executing a series of database operations based on previously generated SQL commands. These might include operations like insert, update, select, or delete. After executing each SQL statement, the database updates and returns the results. Importantly, the decision to move to the next memory operation step is based on the results of previous SQL operations. We keep going until we've completed all necessary operations on the memory. Finally, we have the response summary stage. Here, we create a final response for the user based on the results from our chain of memory operations. The final response is what the user will receive as the output from ChatDB. For more technical insights, refer to our detailed algorithm representation that demonstrates the step-by-step procedure of ChatDB in response to user input. However, In essence, it follows the sequence of the three stages we just outlined. Process input, manage memory through the chain of memory, and then generate a response summary to be returned as the final reply. Section summary. The task of ChatDB is to manipulate the symbolic memory, i.e., the external database, to fulfill the user's request. The framework consists of three main stages: input processing, chain of memory, and response summary. The chain of memory approach executes a series of intermediate memory operation steps to interact with symbolic memory, including operations such as insert, update, select, delete, etc., and decides whether to update the memory operation step based on the results of previous SQL statements before executing this operation. Section: Chain of memory. The concept of chain of memory can be thought of as an upgrade to chain of thought, which is about breaking down complex thinking processes into manageable steps. The chain of memory, or COM for short, adds a layer of memory to this process. This memory layer provides a place to store the intermediate steps, offering a powerful way to enhance the performance of large language models, LLMs, when they're working with symbolic memory. In essence, the chain of memory approach takes the user's input and translates it into a series of memory operations. This translation process allows LLMs to interact with memory in a more precise and effective manner, something that's particularly useful when dealing with real-world applications that need to interact with historical data in complex and accurate ways. This is especially true in situations where record-keeping and data analysis are key, such as in a management setting. To improve the effectiveness and stability of our method, we use in-context learning. This means we provide examples of a series of chain of memory steps and chain of thought prompts to guide the learning process. This results in a more robust and precise chain of memory mechanism, which in turn helps LLMs reason more accurately over symbolic memory and handle more intricate situations. There are two main benefits to the chain of memory approach. Firstly, it allows LLMs to carry out intricate database operations more accurately, improving their ability to reason across multiple stages within symbolic memory. Secondly, it lets us break down complex tasks into a sequence of intermediate memory operations. This improves the performance of LLMs when dealing with complicated scenarios involving multiple tables. In other words, it helps LLMs to handle exceptions and unforeseen situations more effectively. This makes the chain of memory approach a very promising tool for real-world applications. Section summary. The chain of memory, COM, approach enhances the reasoning capabilities and robustness of LLMs by providing a symbolic memory mechanism to support the storage of intermediate steps. This approach enables LLMs to better reason over symbolic memory and handle more complex scenarios, making it a promising method for real-world applications such as record-keeping and data analysis in a management setting. By decomposing complex operations into a sequence of intermediate memory operations, the COM approach enhances the capability of LLMs when handling complex, multi-table interactions. Section: Comparison with previous memory-augmented LLMs. Let's compare our system, ChatDB, with previous memory-enhanced language learning models, or LLMs. Broadly speaking, past approaches have had two categories of memory modules for these models. The first type, which we'll call prompt-based memory, stores context and uses a retrieval model to locate content from past interactions most relevant to the current conversation. This content then acts as a prompt for the language model. The second type, called matrix-based memory, employs additional memory tokens or memory matrices as its storage. We will compare ChatDB to these two types of memory based on several criteria. 1. Asterisk memory format asterisk asterisk. This refers to the method used for storing memory. While ChatDB uses databases, prompt-based memory stores relevant interaction content and/or their corresponding vector embeddings. Matrix-based memory, on the other hand, uses extra trainable memory tokens or memory matrices. 2. Asterisk supported operations asterisk asterisk. This is about what actions can be taken to manipulate memory. ChatDB can do things like insert, delete, update, and select data in its database memory. Prompt-based memory mainly supports inserting and selecting operations, but doesn't fully handle updates and deletions. Matrix-based memory allows reading, or selecting, and writing, inserting, updating, deleting, operations. However, we can't explicitly know the exact operations performed by the neural network. 3. Asterisk memory storage asterisk asterisk. This refers to the way data is stored in memory, specifically whether it's structured or not. ChatDB's memory is structured as it uses databases, while both the prompt-based and matrix-based memories are semi-structured. This is because while vector embeddings and memory matrices have specific dimensions and sizes, each individual dimension doesn't have a specific and explicit meaning. 4. Memory execution ****. This focuses on how memory operations are performed, specifically whether they are symbolic or not. ChatDB uses SQL to perform operations on its database memory, which is a symbolic language. This means it performs symbolic executions. On the other hand, prompt-based memory performs selections based on a similarity metric using vector embeddings and uses a language encoder for insertions, both of which are non-symbolic executions. Similarly, in matrix-based memory augmented LLMs, memory operations are entirely controlled by the neural network, resulting in non-symbolic executions. 5. Interpretability ***. This refers to how easily we can understand memory. With ChatDB, memory is stored in a structured and explicit format, and its operations are symbolic, so it's highly interpretable. Prompt-based memory is generally less interpretable because it's hard to interpret vector embeddings. For matrix-based memory, the interpretability is low since memory is completely controlled by the neural network implicitly. 6. State tracking ***. This is about whether the memory effectively tracks the current state of the LLMs. For ChatDB, its memory accurately tracks the current state of the LLMs, as demonstrated in the fruit shop experiment. Each time a record is processed, ChatDB's database memory updates to reflect the latest state of the fruit shop, showing how effectively it tracks its current state. And because it uses symbolic memory execution, ChatDB's memory can easily roll back to any desired timestamp, offering more flexibility and control. In the matrix-based memory approach, the memory is continuously updated by the model itself, enabling it to track the current state of the LLMs. However, the prompt-based memory approach simply stores the historical context and only knows what has happened in the past, without a clear understanding of the current state. When we look at these criteria, we can see the unique features and abilities of ChatDB compared to existing approaches. These comparisons show the benefits of using symbolic memory to enhance language learning models. Section Summary. The section compares ChatDB with previous memory-augmented LLMs based on memory format, supported operations, memory storage, memory execution, interpretability, and state tracking. ChatDB uses databases as memory, supports insertion, deletion, update, and selection operations, stores memory in a structured format, executes operations symbolically using SQL, and effectively tracks the current state of the LLMs. Compared to prompt-based and matrix-based memory approaches, ChatDB's memory is more interpretable and provides greater flexibility and controllability. Section: Evaluation. In this portion of our study, we conduct tests to determine the benefits of enhancing language models with databases as their symbolic storage. The results from our tests show that our model, ChatDB, significantly surpasses the performance of the basic model. ChatGPT, underlining the advantages of integrating symbolic storage. To set up our experiments, we chose to use a database as symbolic storage because it excels at accurately recording and handling historical data, which is crucial in various data management situations. To make our model, ChatDB, adaptable for this use case and to allow for meaningful comparisons with other models, we created an artificial dataset that mimics the operations of a fruit store. To assess the capabilities of the models, we compiled a list of 50 questions, each accompanied by a standard annotated answer. The complexity of these questions varies, with some challenging questions requiring multiple steps of reasoning and simpler ones necessitating only data retrieval from past records. Out of these, 15 are simple questions and 35 are challenging ones. The models answer each question independently. Section Summary. The effectiveness of augmenting LLMs with databases as their symbolic memory was evaluated through experiments, which showed that ChatDB outperformed the baseline model ChatGPT, highlighting the advantages of symbolic memory integration. A synthetic dataset simulating the management of a fruit shop was constructed to enable quantitative comparisons with other models, and a set of 50 questions with annotated standard answers was collected to evaluate the performance of the models, ranging from easy ones that only required retrieving information from historical data to hard ones that required multi-hop reasoning. Section: Model Configuration. We utilized the language model ChatGPT, specifically the GPT 3.5 Turbo version, in our application known as ChatDB. For tuning the model's randomness, we set the temperature hyperparameter to 0. In terms of external memory, we opted for the MySQL database to store and retrieve information. To benchmark ChatDB, we chose the same version of ChatGPT, GPT 3.5 Turbo, as our baseline model, and set the same maximum token limit, which is 4096. Just like with ChatDB, we set the temperature to 0 here as well. For our data, we synthesized a unique dataset which we call the fruit shop dataset. This dataset is designed to mimic the everyday operations in a fruit shop, including actions such as buying and selling goods, modifying prices, and processing returns. We've ensured that the historical records remain error-free, avoiding complications like negative inventory counts. Our fruit shop dataset comprises 70 records, sorted in the order of their occurrence. In total, they consist of about 3.3 thousand tokens, which fits comfortably within the maximum token limit of ChatGPT, which is 4,096 tokens. Why do we have to consider this token length limit? If the total number of tokens in a dataset exceeds the language model's limit, we need to introduce memory mechanisms. However, common memory retrieval methods, which usually rely on vector embeddings, can introduce errors. This can, unfortunately, decrease ChatGPT's performance, which we want to avoid. So, by ensuring our dataset's token length stays within ChatGPT's limit, we evade the need for external memory and ensure optimal performance. It's noteworthy that the token length doesn't significantly impact ChatDB's performance. Therefore, if ChatDB performs better than ChatGPT on a small dataset, it implies that ChatDB is likely superior to a memory-enhanced ChatGPT, even when dealing with larger datasets. Section Summary. The paper describes the model configuration of ChatDB, which uses ChatGPT as the LLM and MySQL as the external symbolic memory. The authors also introduced the Fruit Shop dataset, which contains 70 records of fruit shop management operations and is designed to be within the maximum token length of ChatGPT to avoid using memory and maximize the model's performance. The authors note that ChatDB's performance is generally unaffected by the token length of the dataset, indicating its superiority over memory-augmented ChatGPT when the dataset is large. Section: Processing Records. The first step in preparing ChatDB is to establish the database. We need to create an appropriate database schema, or structure, tailored to the specific task at hand, and set up the necessary tables within that database. This structuring process can be done manually or with the aid of language learning models, LLMs. Once our database is ready, we proceed by processing each entry or record from our dataset individually. We use an LLM controller to manage this external database, which we can think of as a symbolic memory. We'll follow a specific algorithm to perform this. We provide examples of how ChatDB responds to 4 typical actions in the fruit shop dataset: buying, selling, adjusting prices, and returning items. We display these examples in a figure for clarity. It's important to underscore that ChatDB handles each record individually, meaning its performance isn't affected by the total number of records. Also, each database operation conducted by ChatDB is symbolic, meaning it's error-free. Consequently, in theory, ChatDB can process an infinite number of historical records without a drop in performance. On the other hand, for tools like ChatGPT or existing memory-enhanced LLMs, excessively lengthy historical records can considerably hamper performance. For our experiment with the ChatGPT baseline, we kept the records brief, so we just integrated them into the prompt. Section Summary. The first step in processing records for ChatDB is to initialize the database by generating a reasonable schema and creating tables. ChatDB processes each record one by one using the LLM controller, making it insensitive to the total number of records and capable of handling an infinite number of historical records without sacrificing performance. However, excessively long records can significantly degrade performance for ChatGPT or existing memory-augmented LLMs. Section: Answering Questions. When we answer questions, we employ a system called ChatDB, which does not need to use records within the immediate question. Instead, we process and store the necessary data in a form of symbolic memory. We use a specific method, or algorithm, which makes use of SQL, a programming language designed for managing databases, to carry out a series of inquiries into the database. These actions help us answer your question. On the other hand, we have another model called ChatGPT, which takes a slightly different approach. It includes records directly within the question prompt. We've tested both models, and our experiments show that ChatDB is significantly more accurate than ChatGPT. While ChatGPT does a good job with simpler questions, it struggles with complex ones that require more extensive logical jumps and precise calculations. This results in a lower success rate with these types of questions. On the other hand, ChatDB excels at them, illustrating the benefits of using a database as a symbolic memory system. This strategy not only minimizes the risk of accumulating errors but also enhances the model's ability to handle complex reasoning and calculations. We've included several examples where the two models answer questions for a direct comparison. In all these instances, ChatDB provides the correct answer, whereas ChatGPT fails. Specifically, ChatGPT tends to struggle with calculating total prices in sales transactions. At times, the logic behind the calculations might be correct, but the end results are wrong, while at other times, even the logic itself is flawed. This problem with identifying all valid sales transactions leads to errors. Furthermore, ChatGPT often makes one mistake after another, leading to an accumulation of errors. In contrast, ChatDB performs exceptionally well in these cases. Initially, it uses SQL operations on the database to store all the information in an orderly manner. When answering questions, it generates SQL queries to extract the needed information. Our examples showcase how effective ChatDB is at solving problems, even when it requires 1, 2, or 3 consecutive steps of memory referencing. ChatDB's strengths shine in 2 main areas. 1. Through its chain of memory approach, it can break down complex problems into smaller, more manageable steps. The result of each step is stored accurately and used in subsequent steps, greatly aiding in complex reasoning. 2. It uses symbolic memory for precise calculations and operations. Many of the tasks related to calculations are delegated to the external database through SQL, ensuring the accuracy of each step and minimizing errors. In conclusion, by employing external databases as a symbolic memory tool, our ChatDB model significantly outperforms ChatGPT in our experiment. Section Summary. The ChatDB system utilizes SQL statements to process records and store information in symbolic memory, allowing for accurate multi-hop reasoning and precise calculations. In contrast, ChatGPT includes records as part of the prompt and struggles with hard questions that require multi-hop reasoning and precise calculations, resulting in low accuracy rates and error accumulation. ChatDB's chain of memory approach simplifies complex problems and delegates calculational tasks to the external database, ensuring accuracy and preventing error accumulation. Experimental results demonstrate ChatDB's superiority over ChatGPT in accuracy and effectiveness.